Okay, so here we are. We're going to start with measurements in units and the unit breakdown. What exactly does that mean? Before we do that, I just have to reiterate that in physics, specifically for distance, we always use meters, we always use kilograms for mass, and we use seconds for time. Not always, but quite often. And those are what we consider our base units for physics, or most common units. Okay, so really important that you know that. Of course, we're sticking to the System International units or metric because it's far superior to imperial. So what is a derived unit? That's basically when they came up with new things that they needed new units for. They're like, okay, well, we can't have this mess of units, so we just came up with something new. Okay, so we still have base units like kilograms, meters, and seconds, but then they needed a unit to express force. And so they named that after Isaac Newton, and we call it a Newton. So here we have a capital N, and that's what we did. But it's actually made up of a bunch of different units. Now, as we go through physics, you'll see why more and more, why these are the units that it's made up of. But at this point, you should just know this table, okay? So a Newton is made up of kilograms times meters per second squared. Okay? A joule, that is the measure of energy or work, and that is newtons times meters. That's what that dot there means. It means multiplying. Okay? A watt is joules per second. Now, if you look at joules and watts, so joules is made up of newtons and meters, but newtons are made up of smaller units. Watts are made up of joules per seconds, but joules are made up of newtons, which are made up of smaller units. So you see where I'm getting here, where we can break down the joule and the watt and the pascal into even smaller units. So if I actually want to know what the base units are that are a part of a joule, I need to put in what the newtons are for joules and then do some canceling or multiplying or some stuff to figure out what are just the base units that joules are composed of, okay? So we're gonna go ahead and write pascals in base units. So as we saw here, pascals are newtons per meters squared, okay? So I'm gonna write that as a proper fraction now. So we know that newtons broke down into something else, okay? Newtons broke down into kilograms times meters per second squared, okay? So, again, Newton was a kilogram times a meter per a second squared. Okay, and then we still have that per meter squared, but instead of doing that, I'm going to multiply by 1 over meter squared, and you're going to get y very soon. It's the same thing, right? Newtons per meter squared is the same as newtons times 1 over meter squared. So it's just a better way to write it because now I can do some canceling of stuff and it'll make my life a lot easier. So again, I need to bring this whole thing with the kilograms per meter squared together with the 1 over the meter squared. I need to bring all that together. What can I do? Well, it looks like we have a meters right here and a meter squared right there. So one of these guys cancels out with one of those, right? Because meters divided by meters squared. Remember, you just subtract the exponent, so that's meters to the power of 1 minus 2, which is -1, which is the same as 1 over meters, okay? So that's what's happening there is we can cancel those out. And once we do that, let's kind of figure out what do we have left on the top, what do we have left on the bottom. So here we have kilograms, there was not touched, and that looks like it's the only thing left on the numerator. So in the denominator we have seconds squared per just meters, because we don't have meters squared anymore because that guy canceled out. And there you go, that is pascals in base units. And that's what I mean base units. It means it's made up of kilograms, seconds, and meters, and that's it. So if I want something broken up into its base units, it's just asking how is this made up of kilograms, meters, and seconds, okay? And all of these units you can do that with. So you'll have to do joules and watts all by yourself and see if you can figure that out. Let's move on to proportionality. This is a concept that's really, really important for you to understand in physics. And so that's basically just saying what's going to happen to one variable if another one changes, right? So, for example, what's going to happen to velocity if you have to cover the same amount of distance, but now in half the time? What do I have to do to my velocity to make sure that I can cover the same distance in the half amount of time that I did before? So that's what I'm talking about when I'm talking about proportionality. So how do you do that? Well, if I'm, for example, looking at velocity and time, but distance remaining constant, then I'm just going to ignore distance and I'm just going to look at velocity and time and where they're placed in their equations. Okay? So for example, let's look at the formula for work. Work is equal to force times displacement. You saw this in Science 10. So if I want to know how is work just proportional to force, well, if displacement is staying constant, and I want to know, well, if I double the force, what's going to happen to the work? I need to know the proportionality between the two of them. So here I'm going to ignore displacement, pretend it's not there. Oh, work and force are directly proportional. So I'm going to replace this equal sign with a little fishy sign, and that means proportional to, okay? So this means proportional to, okay? So that's how we figure out the proportionality between force and distance. That is called a direct proportionality, okay? Because really, what does that mean? It means something happens to work, the same thing happens to force. And then if I want to figure out what's the proportionality between work and distance, I ignore the force and say, okay, you're not there, and just look at where work and distance are placed. Again, they're both just like right across from each other. Nothing's being squared, nothing's being divided, or anything like that. So therefore, work and distance are also directly proportional, okay? So what does that mean? It means if I keep force constant, but I double the distance, what happens to the work? Oh, it doubles. If I triple the distance, what happens to the work? It triples. If I triple the work, what happens to the distance? But the force is the same. Oh, that means I must have tripled the distance. That's all that means when we're talking about direct proportionality. So what happens to work if force doubles? Well, again, if this guy's doubling, then this guy also has to double because they are directly proportional. So when you see a proportion like that, where there's nothing happening to the work or the force, nothing's being squared or anything like that, then we know it's exactly the same. So if I double the work, I double the force. Okay, so there we go. That's how proportionality works. Now that's direct proportionality, so that one is nice and easy. Let's do another example where we don't have something that's quite as nice and easy. So here's an example of, or here's a simplified version of acceleration is equal to velocity squared divided by the radius. So this is actually circular acceleration, which you guys don't know about yet, and that's okay. So just trust me, this in some situations is a equation for acceleration, just a very certain type of acceleration. So I want to know, how is acceleration proportional to the velocity? How's acceleration proportional to the radius? So again, if I want to look at how is acceleration proportional to velocity, I'm going to ignore the radius. I'm going to say, pretend, okay, you're not there. Okay, and then look at that. Look what's happening between the two of them. It says A equals V squared. Obviously it doesn't, but that's its proportionality statement, okay? Is that acceleration is proportional to velocity squared. So what's going to happen? What happens now if velocity doubles? Does this acceleration just double? No, because they don't have direct proportionality. If velocity is doubling, then you have to square that. So 2 squared is 4, so that means acceleration is quadrupling. And we're going to go into that a little bit more. Okay, so that's how we get the proportionality statement between A and V. Now I want the proportionality statement between A and R. So what am I going to do? I'm going to ignore V. Say, no, you're not there. Now this is kind of weird because it's on the bottom of a fraction and there's nothing on the top. So we're just going to put a 1 up there. Okay, and so again, we just ignore the other thing. But in this kind of situation, we put the 1 up there. And so here we get that acceleration is proportional to 1 divided by r. So this is called an inverse proportionality, where if we do something to r, the exact opposite happens to a, because they are inversely proportional, right? One's on the bottom of the fraction, one's at the top of the fraction, right? Think of this as a over 1, and so a is on the top, r is on the bottom, so exactly the opposite. So if I double r, a is going to half. If I triple r, a is going to be 1/3 as much, right? That's how that kind of proportionality is going to work. So that's how you figure out proportionality. Honestly, ignore everything else in the equation that's not part of the proportionality statement you're trying to figure out. So the question I now want to answer is, what happens to A, acceleration, if V is 5 times as much? Okay, so I'm making V 5 times as much. So I have A proportional to V squared. So remember what's happening to V, I'm making it 5 times as much. So I'm actually going to put 5 there. And then what happens to V? I square it. Okay, so what does that mean? Well, first of all, what's 5 squared? That is 25. So A is now 25 times bigger. Okay, so that's all you got to do. Is if you want to know how proportionality works, if it's not just direct, then you have to just put the number in for the variable, okay? So that means A will be 25 times larger. Okay? And that's how proportionality works if it's not just like a nice direct thing, okay? So finally, I just want to know what happens to A, acceleration, if r is 1/4 as much. So again, here I have that A is proportional to 1 over r. So now r is becoming 1/4. So 1 over 1/4, what the heck is that? Well, keep in mind that's the same as saying 1 divided by 1 over 4. What do you do when you're dividing by a fraction? You multiply by the reciprocal. So that's actually the same as saying 1 times 4 over 1. Hey, that's just 4, right? So that's actually what's happening. If r is 1/4 as much, then a is 4 times as much. So you see that inverse proportionality, right? So whatever happens to r, the opposite of that happens to a, okay? R was quartered. That means a is 4 times as much. Okay, and that's how proportionality works. So good luck with that.